Section 4 is about solution concentrations. Your learning goal is to be able to calculate the concentration of a solute in a solution and use concentration units to calculate the amount of solute or solution. Our body fluids contain water and dissolved substances, including glucose, urea, and electrolytes such as potassium, sodium, chloride, magnesium, and so on. Proper amounts of each of these dissolved substances and water must be maintained in the body fluids. Small changes in electrolyte levels can seriously disrupt cellular processes and endanger our health. Solutions can be described by their concentration, which is the amount of solute in a specific amount of that solution. Think about if I made a Kool-Aid solution. Let's say that I had 2 containers with the same amount of water, and in one container I put 1 scoop of Kool-Aid, and in the other I put 10 scoops of Kool-Aid. One is going to be really diluted and taste terrible, and the other one's going to be really concentrated. Might also taste terrible. But that is what concentration is, but it would be measuring it, weighing out the specific amount of solute, and knowing the specific amount of solution, we can find the concentration, which is just a simple division problem. The amount of solute divided by the amount of solution. Here's a summary of different types of concentration expressions and their units. The first one is mass percent, and that's when we would measure our solute in grams and our solvent in grams, and we would look at this mass percent. So the mm just tells us mass, and we know mass is in grams. And I'm going to skip here. If we look more specifically at mass percent and what it describes, we look at the mass in grams of solute per 100 grams of solution. And notice that we take the mass of the solute in grams divided by the mass of the solute plus the mass of the solvent. So it's the whole solution we need. It's like saying the part divided by whole. And obviously if I just had the mass of the solute divided by the solvent, that solvent is not the whole mass of the solution because we would be missing the mass of the solute. So don't forget this part where we add the mass of the solute and the solvent for that denominator. The next part is the volume percent. Notice VV, that means the volume is measured for the solute in milliliters and the volume for the solvent, both in the same units. Mass volume percent, again mass is in grams, volume is in milliliters, and molarity, capital M, we have our solute measurement in moles and our solvent in liters. Back to the mass percent, let's look at a sample problem. When water is added to 8.00 grams of KCl to form 50 grams of a KCl solution, the mass percent concentration is 16%. Notice it says mm, which is mass. I could find a few things from this. Notice I have a beaker here sitting on a scale, and we put 8 grams of that KCl into that beaker, and then it said that we formed 50 grams of solution. So then we added enough water to make that scale go up to 50. I could figure out how much water was added by simply doing 50 minus 8. That would tell me that I used 42 grams of water, which is my solvent. So this bottom denominator here, this 50, is 8 plus 42. So I did my part, my 8 grams of KCl divided by 50 grams, times it by 100, and I got 16%. Why don't you pause the video here and try this sample problem, looking at the mass percent of sodium hydroxide in a solution prepared by dissolving 30 grams of sodium hydroxide in 120 grams of water. Step 1, it said mass percent. So mass percent, we need to just refresh mass, so we need to know grams of solute and grams of the whole solution. So we will take that 30 grams of NaOH and add the 120 grams of water to get 150 grams of the sodium hydroxide solution. That would be my denominator. And the mass of the solute, the 30 grams, divided by the 150 gram solution, and times that by 100, we would get 20.0% NaOH solution, and we started with 3 sig figs. We're going to end with 3 sig figs. Why don't you try this next sample problem? The topical antibiotic ointment Neosporin is 3.5% mass, neomycin solution. How many grams of neomycin are in a tube containing 64 grams of ointment? Pause here. Let's get started. We were told that we had 64 grams of the ointment, and we want to know how many grams of neomycin are. So we don't know the solute, but we do know that the whole solution is 64 grams, and we do know that our mass percent, that we do our solute divided by the solution, times that by 100, and we were told that that was a 3.5% mass percent. Now let's work backwards to find x. If I'm timesing this by 100, that means I need to divide both sides by 100. So 3.5 divided by 100 would give me 0.035. Now I just need to solve for x. I'm going to cross multiply again. This is the same as 0.035 over 1. So I'm going to multiply these two together and multiply these two together. X times 1 is x. And 64 times 0.035 should give me 2.24 grams of neomycin. But I'm going to look at what I was given, and I was given two significant figures and two significant figures. So I'm just going to finish with 2.2 grams of neomycin in the solution. I like to go back and always double check. If I did 2.2 divided by 64 and times it by 100, that should give me 3.5%. Now, volumes of liquids or gases are easily measured. So the concentrations of their solutions are often expressed in the volume percent. We interpret a volume percent as the volume of solute in 100 milliliters of solution. The volume percent describes the volume of solute in milliliters or liters. Those are the common volume units. The volume of the solution in the same units as the solute. So we need to make sure that we're either both in milliliters or both in liters. And again, we just take the volume of solute divided by the whole solution, so the two added together, and times it by 100. Very similar to mass percent, but mass percent was in grams, grams divided by grams. Volume percent is either milliliters or liters divided by the same unit. Let's say that we have a bottle of vanilla extract, and it says right on that bottle of vanilla extract that this is 35% VV, volume alcohol. This means that the bottle contains 35 milliliters of ethanol, which is the solute, per 100 milliliters of vanilla solution. Just like in that last example when I said 3.5% neomycin solution, I was able to say, oh, well then there's 3.5 grams of neomycin per 100 grams of ointment. Let's say that I have a bottle that contains 59 milliliters of lemon extract solution, and the extract contains 49 milliliters of alcohol. What is the volume percent of the alcohol in the solution? See if you can set that up. Hopefully you took that alcohol, which is the solute, divided by the whole solution. So 49 divided by 59, again my milliliters will cancel out, times it by 100, and I would get 83% volume alcohol solution. Let's look at that mass volume percent concentration. The mass of solute in grams per 100 milliliters of solution. This one is going to be more specific, and it's going to be grams per milliliter, and because it's percent, we also times it by 100%. The mass volume percent is widely used in hospitals and pharmacies for preparing medicines and intravenous solutions. A 5% mass volume solution of glucose contains 5 grams of glucose in exactly 100 milliliters of solution, and has a combined volume of glucose and water to make 100 milliliters of solution. Let's try this sample problem. We have potassium iodide solution. It may be added to a diet that is low in iodine. A Ki solution is prepared by dissolving 5 grams of Ki in enough water to give a final volume of 250 milliliters. What is the mass volume percent of the Ki solution? Pause the video and try and set it up. First thing is to see what expression we'll use. Mass volume means we will take the mass of the solute divided by the volume of solution, and we want grams and milliliters. So then we'll just take our 5 grams of Ki divided by 250 milliliters, both have two significant figures, and then times it by 100, and we get 2.0% mass volume Ki solution. And the last is molarity. Molarity is used when working with solutions, and it tells us the moles of solute per liter of solution. So we're just taking that last one a little bit further because we had grams, but we know if we have grams of anything, we can get to moles of it by simply taking that grams and finding the molar mass of Ki. So I would look at the periodic table and take 1K plus 1I, and I would go my 5 grams of that. I would have the molar mass on the bottom for every 1 mole. And then if I had milliliters, I can convert to liters by dividing by 1,000. Let's look at a sample problem. If I had 1 mole of sodium chloride, it's dissolved in enough water to make 1 liter of solution. The concentration of the solution will be 1.0 m, and that m means moles per liter. Again, we're just taking moles of solute divided by liters of solution. What is the molarity of 60 grams of sodium hydroxide in 0.250 liters of NaOH solution? Try that. First thing I thought of was that 60 grams, if I want molarity, I got to get to moles. So I found the molar mass of NaOH was 40 grams of NaOH in 1 mole of NaOH. So I had to do this step first and go from grams to moles. 60 grams, again I have to have grams on the bottom to cancel those out. 60 times 1 divided by 40 gives me 1.5 moles of NaOH. That's my top, my numerator, and I need to divide it by liters of solution. And I am given liters of solution. So the last step is just taking my 1.5 moles of NaOH divided by 0.250 liters, and I would get 6, I need 3 significant figures, 6.00, capital M, which stands for moles per liter, of NaOH solution. Can you work backwards? We want to know how many liters of a 2 molar NaCl solution are needed to provide 67.3 grams of sodium chloride. Pause the video. The first thing I noticed was that I'm told that I have a 2 molar NaCl solution, and that capital N means moles per liter, and we want to know liters, so we want to find out the denominator. Now the numerator here is in grams. I need my numerator to be in moles. I'm going to find the molar mass of 1 Na plus 1 Cl, and I got 58.44 grams of NaCl in 1 mole of NaCl. So 67.3 times 1 divided by 58.44, that gave me 1.1516 moles of NaCl. Now let's write it out to figure out how to find how many liters. That liters is my denominator. So I put my moles on top, divided by X is equal to that 2 molar solution. I don't like working with fractions, so I'm going to cross multiply here and do 2 times X. 2 is the same as 2 over 1, right? So I'm going to say 2 times X is equal to, I'm going to cross multiply here, 1.1516 times 1 is 1.1516, and then I'm going to divide both sides by 2 to get X by itself. And X should equal 0.576 liters of NaCl solution. We started with 3 significant figures there and 3 significant figures there, so we wanted to end with 3 sig figs, 0.576 liters. Here's a chart looking at conversion factors and concentration expressions. If I told you 10% mass of KCl solution, the meaning of it would be that we have 10 grams of KCl in 100 grams of KCl solution. That also provides us with conversion factors. I can say that, hey, there's 10 grams of KCl in 100 grams of solution, or I can say that in 100 grams of solution I have 10 grams of KCl. Take a minute to look and see what that 12% volume ethanol solution means, 5% mass volume glucose solution is, and what 6.0 m, or molarity, of HCl solution means, and those conversion factors. And then look at the review to make sure you understand everything.